Hi everybody, welcome to Math with ACE, specifically Statistics with ACE today. We are going to be breaking down the empirical rule on the standard normal distribution, which is also called the 68, 95, 99, 7 rule. You can call it both. It's whatever you want to call it. Just be familiar with both in case whoever you're working for, your teacher, calls it one of the two. Okay? To start, we need to break down the picture that we have here. This is a standard normal distribution, and in a standard normal distribution, right down the middle of our distribution that sums to one whole, we have the average. We would expect the average value to be right in the middle, okay? On either side of it, from calculus, we are able to determine at that inflection point, we are able to determine that that's one standard deviation in these curves. So this is the mean plus one standard deviation, which is one z-score to the right. Remember, a z-score standardizes your values based on the mean and the standard deviation of your distribution. The next line that we have here is two standard deviations to the right. And the next line is three standard deviations to the right. So these are standard across the board for any normal distribution, regardless of how skinny or wide it is. If it's normally distributed, this is true. To the left, we have one standard deviation below the mean, two standard deviations below the mean, and three standard deviations below the mean. In a standard normal distribution, our special distribution with a z-score of 0, we have 1, 2, and 3 to the right, -1, -2, -3 to the left. And z-scores are measured in standard deviations. So we are one standard deviation above the mean, two standard deviations above the mean, three standard deviations above the mean, and so on. So z is normally distributed with a mean of 0 and a standard deviation of 1, using that notation. Now, the empirical rule tells us certain things about 1, 2, and 3 standard deviations away from the mean. So the empirical rule, which is also called the 68, 95, 99, 7 rule, and actually these are dashes, tells us that 68% of a normal distribution is within one standard deviation. And again, this is based on calculus. So mathematicians have run the numbers. They've determined that this is true always for normal distributions. So what that is saying is that 68% fall within one standard deviation. So that is +1 to the right and -1 to the left of the mean. Well, if it's the 68, 95, 99, 7 rule, how many fall within 2? 95. So that is saying that here, at +2 standard deviations and -2 standard deviations, 95 fall within that. So I have 95% of the distribution is within. So this is what we would consider usual. Anything that's outside that typically is what we would consider statistically significant. And then what do you think the percentage is for 3 standard deviations? If you guessed 99.7, you would be right. So +3 standard deviations here, -3 standard deviations here is 99.7% of the data. We can use that knowledge to then break down each component. If we know that 68% fall within that one standard deviation, that means it's equally split because this is a symmetric distribution. So I can cut 68 in half. 68 divided by 2 is 34. That means that 34% are to the left and 34% are to the right. You could also write that as 0.34 if you're dealing in decimals. Those are equivalent. What about 95? Well, 95 cut in half is 47.5. But that little slice right there is not 47.5. That does not make sense to have a bigger portion of 34 be smaller than a larger portion of 47.5. And the reason is 95 is this whole set. Well, we've already accounted for this portion right here. So what is left? So 47.5, if we take away the 34 that we've already accounted for, that gives us 13.5. That means that in this section to the left, that's 13.5% or 0.135. What about 99.7? 99.7 divided by 2 is, I believe, 49.85. Yes. However, we've already accounted for the 95, which was split into 47.5. So we need smaller portions. If we subtract away the 47.5 we've already accounted for, we get 2.35. So this is 2.35%. It doesn't really fit under the curve anymore, so I'm writing it above. And as a decimal, that is 0.0235. It's small. Okay, so 100 is the whole distribution. So outside those values of 99.7, that is 0.3%. 0.3 cut in half is 0.15%, or as a decimal, 0.0015. Don't mix and match your decimals and your percents. Use one format and stick with it. Okay. I can use this to answer questions. And in my class, I use these values. If you go online, you can get values that are more specific to the 100th. I use these values. But I could ask you, what is the probability of being between -1 and 2 in z-scores? So if I wanted to know, I could say, what's the probability of z being less than -2? What's the probability of being between -1 and 2? What's the probability of being more than 3? Those are all types of questions I can answer with this distribution. I can even go backwards and find a value based on a percentage. So here, if I'm trying to approach the z is less than -2, I go to -2 and I follow the sign of less than. And then I add everything up. -2, my percentages were 0.15% and 2.35%. And when you add those together, you get 2.5%. So the probability of being less than 2 negative standard deviations away from the mean is only 2.5%. What about greater than 3? I would go to 3, draw a little arrow, and add everything that was to the right of my arrow. Not just one section, it's everything that's to the right. Well, the only thing that's to the right of that is 0.15%. Very unlikely to be more than 3 standard deviations away from the mean. It's unusual. What about from -1 to 2? In this case, I'm looking for between the two of them. So to the right and to the left of, to the right of -1 and to the left of 2. And so I want all of these values in there. That is 0.34. I'm going to be consistent like I told you. That is 34% plus 34% plus 13.5%. That gives me 81.5%. I hope this helps understand the breakdown of where these numbers come from, how you can use it. You can also use the empirical rule in a non-standard normal distribution. So what I mean by that is, if I have a problem where I'm specifically dealing with a given mean and standard deviation, for instance, let's say that the average number of ounces in a soda can is 12 with a standard deviation of 0.1. That means I'm talking about X is normally distributed with an average of 12 ounces and 0.1 standard deviation. I can label my curve. I'm no longer dealing with the z-score values, but my mean always goes in the middle. So 12 goes in the middle. And then I use my value of standard deviation to calculate what goes to the right. Each of these distances needs to be 0.1 apart because that is what my standard deviation is. And you're just using addition and subtraction on a number line to get higher and lower. So what is 12 plus 0.01? That gives me 12.1. Plus, not 0.01, plus 0.1 gives me 12.2. Plus 0.1 gives me 12.3. Then I can subtract to go the other way. 12 minus 0.1 is 11.9. Minus 0.1 is 11.8. Minus 0.1 is 11.7. So I could ask you, what is the probability of being between 11.8 and 12.2 in a can of soda? Okay, so you can use this with z-scores and you can use it with other distributions. It's just important to draw it out, label it, and then shade in the area you're talking about and add those pieces. Thanks for watching.